Hello and welcome to the video on conservative vector fields. So first of all, I just want to go over a term that might pop up every now and then. So far we've learned line integrals, the scalar kind and the vector line integrals. So as far as the vector line integrals, we have something that looks like this, as it appears in your book, or even something like this, which I think is a little bit more, which exemplifies what's going on here, taking the tangential component of the vector field f. But anyways, so aside from that, there's a special term for when your curve is closed. So closed is not the terminology, but closed means when your start point is the same place. So start point is the same as, so equals basically, your end point of your curve. So an open curve would look like this, okay, because start and end are separate. But a closed curve, let's say here's your start, and then you go around and you end up at the same spot. So this is a closed curve. As you can see, it encloses a space. Okay, so when this happens, the line integral is called the circulation. So this is called circulation. Well, I'll write that after. Called circulation of f. F is your vector field around C, your curve. Okay, so there's separation here. Okay, and then the way it is written sometimes is just like up here. Okay, but then they add this circle just to tell you that it is closed. Okay, that the start is the same as the end point. All right, so this is just something to keep in mind. And then now I'll go on to the fundamental theorem for conservative vector fields. So I'm going to abbreviate a little bit and say fundamental theorem of, not of calculus, but fundamental theorem of conservative vector fields. Okay, and in this case, conservative vector fields satisfy the following. The f vector field is the gradient of some potential function v. Remember? Okay, so two things hold here. So if C prime of, or C of t is a path from point P to point Q in domain D, okay, then the following is true. So here's your curve, right? And we're taking the vector line integral around it, so something like that, or I'll denote it like this. It's the same thing, okay? This represents the same thing. Then we have that according to the fundamental theorem of conservative vector fields, the following is true. That the line integral around, or the circulation around the curve, or no, not circulation, sorry. This line integral, so this thing here, is equal to v, our potential function, evaluated at Q, minus v evaluated at P. Okay, so and I'll do a proof on the next, well, somewhat of a proof on the next slide to explain this a little bit more. But and the second part to the fundamental theorem of conservative vector fields is that if C is closed, if our curve, I'll just put C, is closed, so in other words that means P equals Q, then the following is true. Then our line integral, so now this is a closed curve, right? Because if it's closed, then our line integral for conservative vector fields equals technically v, same thing, right? But in this case, q and p are the same, so we could just as well write v of p minus v of p again, which equals 0. So what this means is that the circulation around closed paths is 0 when dealing with conservative vector fields. So I'll just abbreviate conservative, and then I'll write vector fields. Okay? Alright, so now I'm going to prove the first one, and then it kind of just naturally leads into the second one. That's like common sense kind of thing. So, as far as the first one goes, if we have a conservative vector field, we know that the f has to equal the gradient of v. Okay? So, in this case, what we can do, usually our vector line integral looks something like this, okay, which can also be written as the following. So then we have, not a, sorry, that's supposed to be a c. So c, and then, well, I guess I could put an a. So from a to b, right, those are the bounds for t, and we've seen this before. I'm just going to rewrite the form for a vector line integral. So we have something that looks like this, right, and then the dt. But now we can just as well replace gradient of v in for f. So that would look like the following. We would have a to b, and then instead of an f, we now have a gradient of v, c of t times c prime of t dt. Okay, and what this is, as you might recognize it, that's actually the chain rule. So this is actually the derivative with respect to t of the function v, the multivariable function, of course, of v of c of t. Okay, so that includes the parameterized curve in it. So what this is, so this is chain rule, kind of chain rule. You might remember this from 32a, chain rule here. So what we can do now is just sub all of this back in for all of that. Okay, so basically what we're going to get is integral from a to b, and now we have d dt of v of c of t. Sorry, so many parentheses. Anyways, dt. Okay, so when this happens, now we have a derivative inside of an integral, so we all know what happens when that is there. That due to the fundamental theorem of calculus now, when you have a derivative and an integral in the same expression, they kind of sort of cancel in a way. But what you do is, this is the function being derived. So now this is equal to the function being derived evaluated at the top bound, so b, minus the function evaluated at the bottom bound, the lower bound. Okay, so from this step to this step, we use the fundamental theorem of calculus. Okay, and as we know, this is the end point. Okay, end point, and this is the start point. So we could just as well say, like, okay, here's the start and here's the end. So this is when c of a, and this is our c of b, and we could just as well call this start point P and end point Q. So that would just be the same as V of Q minus V of P. Okay? So anyways, that's where that comes from. And an important part here means, an important part of this whole theorem is that, as you can see here, it only depends, the line integral, the entire line integral, when dealing with conservative vector fields, actually only depends on the start point and the end point. Okay? Anything in the middle, like even if we took different paths and started and ended at the same points, we would get the same line integral. Okay? So what this is called is a special terminology called path independent. Path independent. independent. And that's kind of self-explanatory. I just said the line integral does not depend on the path that you take from start to finish. So you could even go all around and then just come back to the same ending point and you would get the same thing. All right? Okay, so now let's do an example dealing with conservative vector fields. So what we're going to do now, example here, we're going to find a potential function for the following. For f, the vector field that is described by 2x plus y and then an x. Okay, and use to evaluate, so a two-parter, use to evaluate the line integral, the vector line integral of this, okay? And then where C, okay, this is still given, where C is a path from, and they give us 1, 2 to 5, 7. So in this case, we can kind of consider this as P. That's point P, and this is point Q, right? And we have our vector field given by that. So what we want to find, well, so this is the first part, right? Find the potential function. And then we have to evaluate the line integral. So let's focus on part 1 right now. So we have our F, our vector field. So potential function is basically, so here's the relation given by the definition of a conservative vector field. So that would be that, right? So this implies that since we only have two components here for our vector, all we need are the first two. So we have partial v, partial x, and partial v, partial y. Okay, so what we want to find is what is our original scalar potential function. What's our potential function? Potential function is what? Okay, so I'm going to go through the process of how you would find one, a systematic way, because there is a way you can just like look at something and then just guess what it is. That is a way. Sometimes they're easy enough to figure out just by looking, but sometimes it doesn't work out that easily. So I'm going to show you the systematic way of solving. So what you're going to do is basically the first component of your vector field, vector, is going to be equal to the partial v partial x. That's what it should be equal to, right? If your vector field is conservative. So I'm going to say that equals 2x plus y, okay? Because they're both in the first spot, or the first component of f, right? So I'm going to set those equal. And then what we're going to do is integrate with respect to x, okay? Integrate with respect to x so that this side just becomes v. The left side just becomes v. So we're going to integrate with respect to x on both sides, okay? So on the left side, that becomes v of x comma y. And we don't write x comma y comma z because there is no, we're not dealing with a z component in this problem anyways. So what we have on the left is this, and then on the right, you just integrate. So with respect to x, so that would be x squared plus xy. And here's the important part. Then you have to have a plus some function only of the other variable, of y in this case. Because if you think about it, if you go the other way, and we look at this function here, this potential function, then if you're differentiating only with respect to x, then we would just go backwards to this, and whatever y terms we have, those are just considered constants, so those would go away when you derive. But anyways, so this is very important, okay? So at this point, this isn't our potential function definitely. It is a candidate for one, okay? I guess you could say it's like a potential function, but anyways, then that gets weird. So this is like one part of it, okay? So we're here right now, but now we have to utilize our second component, okay? So we're going to set those equal. So we have partial v partial y equals x, okay? And we're going to do the same thing here, except for now we're integrating with respect to y, because we want the left side to be just our v of xy. Okay, so we're going to do the same thing on the right, integrate with respect to y, and on the left here we get v of x comma y equals, and if we're integrating with respect to y on the right side, we just get xy plus some other function. Now it's not of y, but now it's of x, okay? Because x was just considered a constant in both the integration and differentiation if you go back, okay? So now we have these two separate functions, all right? So now what's going to happen is, I'll continue on the next slide. Just make sure you have these written down, and I'm just going to rewrite them anyway, so it doesn't really matter. But okay, so here was the first one that we got. We got v of x comma y equals x squared plus xy plus some function of y alone. Okay, and the second thing that we got looks like this, and I'll rewrite it a little bit differently. I'll space it out so we have something like that, and then plus I'm going to write the function of x right in front there so you can see how it lines up. So this is the way I do it from here, is you just see what lines up where. So this xy and xy, that has to be in both, and it already is. So our final v of xy is definitely contains that, and it definitely has to contain this x squared, okay, which also takes care of the g of x from this equation. So basically, your final answer for your potential function is going to contain everything that needs to be in there. Like a combination of all the equations that you found, like each individual one, just put together into one. Okay, so basically in this one, like I said, the xy term, this middle thing, that appeared in both, so that's definitely going to be in there. The x squared from the second equation. So the x squared from the first equation was represented by g of x in the second equation, so that definitely has to be there. And then f of y here, this last one, it doesn't really need to be there, so we could just make that a 0. So plus 0. And I'll show you, so this is x squared plus xy. That would be our final answer. And you can always feel free to check. So take the partial with respect to x. So if you do the partial derivative, you get 2x plus y, which is good. That was the first component of our vector field. And then we'll do partial with respect to y now. And then we get 0 plus x. So that would just be x, which is also good. Okay? So in your potential function, you really only need the minimum amount of terms that are necessary, but you can also add like the plus c. That's just like a universal constant that we always use in integration, in indefinite integrals. So anyways, we saw what matched up, and this is our final product for our potential function. Okay? And then this extra c, like, that's just, if you want it there, you can. If not, it's not necessary. Not necessary for the purpose of our calculations. Okay? Alright, so that was the first part. We found our potential function, and I'll just rewrite it here just for future reference. So keep that in mind. And now we'll solve the second part. So part 2 of the question asks to find the vector line integral given the vector field 2x plus y comma x. Okay, and then they also gave us that the curve goes from the point 1, 2 all the way up to 5, 7. Okay, so this is the start P and this is the end Q. All right, and typically, given this information, we wouldn't really, like, before we even knew anything about conservative vector fields, we wouldn't have really been able to solve this, right? Because we don't know the parameterization for C, and so we can't take the derivative of it and then plug it into the formula and everything. But now that we have the knowledge about potential functions and it being the gradient, f being the gradient and everything, and now that we actually found a potential function which is x squared plus xy, now we know that we can set this equal to v of q minus v of p. Okay? Because we did confirm that f is conservative. Conservative. Okay? So let's do so. So we're going to basically just plug in v of q first. So 5 and 7, and then subtract v of 1, comma 2. Okay? I just plugged in q and p here. And then to get that, this is your x and this is your y. So if we plug those in, we get 5 squared plus 5 times 7. That's our first thing. And then minus, and then we'll plug in, this is our x and y for the second one. So for that, we get 1 squared. Whew, that was weird. 1 squared. And then plus 1 times 2. So this equals 25 plus 35 is 60. And then minus a 3. So our final answer is going to be 57. All right? Okay, so you see here how the characteristic of f being conservative, that helped us a lot, right? Because we could just kind of take a shortcut to the end and use the potential function to use the endpoints, right? And as you can see here, it was path independent. We didn't even have to know what went on during the curve. We didn't have a parameterization for it or anything. So we just used the endpoints to find our final answer of the line integral. Okay. So now we have a theorem.
I got lost. You said this was the way back.